Hello everyone, my name is Li Desuo from Tianjin University. This work, PPT, a pragmatic transport for data centers, is a joint work with Yi Renpang, Ren Jiepei, Professor Ke Qiuli, Professor Xiulong Liu, Xin He, Professor Yitao Hu from Tianjin University, and Professor Wen Xinli from Tianjin University and Huaxia Haorui Technology Company Limited, and Professor Gu Yueliu from Peking University. In recent years, as shown in the figure, the link speed of production data centers grows fast, from 1 gigabits to 10 gigabits, and then to 200 gigabits, and now reaching 400 gigabits and beyond. This turn makes network with higher BDP, shorter FCT, and more flow burst. This required transport to provide higher throughput and lower latency. Existing solutions can be divided in two lines of work. The first line of work is reactive transport, which starts from a small initial window and iteratively ramp up to the right rate. Most of reactive transport are good deployable, but they fall short in utilizing spare bandwidth or optimizing FCTs. Another line of work is proactive transport, which proactively allocs the bottleneck bandwidth. The proactive transport may achieve good performance, but they are challenging to deploy because they require significant modification to TCP/IP network sticks or assume a prior knowledge of flow size. In this work, we aim to explore a new transport can achieve good performance while being readily deployable. We ask, is it possible to leverage reactive transports for the deployment advantage and address their performance issues? There are three key insights in our work. Firstly, DC-TCP is a good start as its good deployability. As shown in the table, DC-TCP is widely adopted in industry and has been integrated into various OS kernels. Furthermore, it is readily deployable as it requires no switch modification and application friendly. Secondly, we think the key culprit is underutilization. When multiple flows share a bottleneck, the spare bandwidth will emerge in two cases. The first case is in slow start phase. The spare bandwidth will emerge in the first multiple RTT of each flow as it converges to the ideal window. Another case is in queue build-up phase. The spare bandwidth will emerge when multiple flows are marked with ECN so that they will cut their window simultaneously. To show this point, we construct a macro simulation and generate traffic under 0.5 loads. As shown in the figure, the link utilization achieved by DC-TCP between 25% and 50% at most of time, and there are 50% spare bandwidth at special time. Thirdly, we think filling the gap to maximum window is good. We have constructed a new hypothetical DC-TCP which sends opportunistic packets to fill the gap to maximum window of each flow. We ran a simulation and found that the hypothetical DC-TCP reduced the overall average FCT by 33% and 40% compared to HOMA and NDP respectively. Moreover, we compared the performance under different window sizes and found that filling the gap to maximum window achieved the best performance. Putting it all together, we designed PPT. To utilize the spare bandwidth gracefully, we designed a dual loop rate control which has a high property control loop and a low property control loop. The HCP follows the behavior of DC-TCP and sends normal packets using DC-TCP congestion control algorithm. And the LCP combines two techniques, an intermittent loop initialization and an exponential window decrease to send the opportunistic packet to gracefully utilize the spare bandwidth left by HCP. The first technique of LCP is intermittent loop initialization. Because of the window dynamic nature of DC-TCP, the spare bandwidth left by HCP appears intermittently. Whenever it appears, PPT opens an LCP and calculates an initial window for opportunistic packet transmission. Specifically, when in slow start phase, PPT setting the initial window to BDP minus the HCP's window size, and for the Q build-up phase, PPT setting the initial window to 1/2 minus the minimal value of alpha and times the maximum window size. Another technique of LCP is the exponential window decrease, which ensures in every RTT, the window summation of LCP and HCP will not exceed the size of maximal window. Especially, the receiver will send one new ACK for every 2 data packet it received, and the sender will send one new LCP data packet for every LCP ACK it received. The sending rate of LCP is naturally cut by half after every single RTT. When packets are marked by ECN because of link congestion, the PPT will ignore all ECN marked ACK to quickly reduce the sending rate of LCP to avoid harming the performance of HCP. As shown in the figure, by combining the above two technicals, PPT can gracefully utilize the spare bandwidth left by HCP. Despite being effective, the dual low rate control treats the small flow and large flow equally in the network. So as shown in the middle example of the figure, the small flows packet will be queued after those of large flows in the switch buffer. This results in extra latency for small flows performance. So flow scheduling is must, but faces two challenges. The first challenge is how to differentiate large flows from small flows with unknown flow size in prior. To meet the first challenge, we propose the buffer-aware flow identification. When user data is copied to the socket send buffer through the system call, PPT will calculate the size of first data copies and compare it with the flow identification threshold to classify the flow as either a non-large flow or a large flow. The efficiency of buffer-aware flow identification has been demonstrated on both memory cache and web search real-world applications, with accuracy rate reaching 86% and 84% respectively. The second challenge is how to prioritize small flows without penalizing overall performance or starving large flows. For the second challenge, we designed the Mary symmetric packet target. It aims to assign higher priorities for flow with fewer bytes and ensuring the HCP traffic will not impact by the LCP. PPT lets the HCP packets use the first four high prioritize, and the LCP packets can only use the remaining four low prioritize. If a flow is identified as a large flow, it can only use the lowest priority in the HCP and LCP priority range. Instead, if a flow is identified as a non-large flow, it can use the other priorities. As shown in the figure, the HCP send packet from the beginning of send buffer, and the LCP send packet from the last bytes of send buffer. In this example, for flow 1, which identified as a large flow, the packet 1 sent by HCP is marked with priority 3, which is the lowest priority in HCP priority range, and the packet 8 sent by LCP is marked with priority 7, which is the lowest priority in LCP priority range. For flow 2, which identified as a non-large flow, the packet 1 and the packet 6 are marked with the highest priority in corresponding priority range. Since flow 1 is identified as a large flow, it will transmit all packets with the same priority. In contrast, for flow 2, as more bytes are sent, its HCP and LCP prioritized will be demoted at the same pace. For flow 2, its priority will demote until it reaches the second lowest priority in corresponding priority range. Combining above two techniques, we propose the buffer-aware flow scheduling. Looking back at this example, in the first step, the ball flow is identified as a non-large flow, and the below flow is identified as a large flow by buffer-aware flow identification. In the second step, the packets are marked with different priorities with Mary symmetric packet tagging. At this point, the packet in switch buffer will reach the same order as the ideal. In summary, through buffer-aware flow scheduling, PPT reduces the extra latency for small flows and protects the HCP traffic will not be impacted by LCP. We have implemented the PPT prototype as an extension to the Linux kernel with about 400 lines of work. At the switch side, we only need to configure ECM marking and strict priority queuing, which is a built-in function in commodity switch. In Linux kernel, we implement the PPT control logic and flow scheduling within the TCP and IP layer. Now we come to the testbed experiment. We use two widely adopted realistic data center workloads, web search and data mining. We construct the all-to-all traffic pattern and the in-cluster traffic pattern to evaluate our PPT. We compared PPT with Homa Linux, RC3, and DCTCP in testbed experiment. We found that the PPT reduced the overall average FCT at least 79%, and the PPT reduced the small flow average FCT at least 84%. We further show the performance under in-cluster traffic pattern. For overall and large flow performance, PPT achieve up to 95.5% and 95.1% performance improvement respectively. And PPT reduce small flows average and tail FCT at least 72% and 88%. To show whether PPT incurs high CPU overhead, we measure the kernel space CPU overhead of PPT and DCTCP in our testbed experiment under web search workload. As shown in the figure, the largest gap between their CPU usage is less than 1%. We also did simulation based on NS3 simulator. We again use two workloads, and we compared PPT with both reactive transports and proactive transports. For overall and large flow performance, PPT reduced the overall average FCT by up to 87%, and PPT reduced the large average FCT by up to 90%. For small flows performance, PPT achieved the best small flow performance under web search workload, and the gap between PPT and Homa average and tail performance for small flows under data mining is 6.3% and 54%. In summary, PPT is a pragmatic data center transport with two components. First, it employs a dual-loop rate control to gracefully utilize the available bandwidth to optimize FCTs. It also has a buffer-aware flow scheduling to scheduling flow without prior knowledge of flow size and without affecting the benefits of dual-loop rate control. That's all. Thank you.